Welcome to In 5 Minutes. In this video clip, we will discuss the receiver or demodulator circuit for pulse amplitude modulation, which is also known as PAM. So in the previous video clip discussed how to generate PAM signal. We will now discuss the second point, which is a demodulator. It's very simple. All you have is something called as holding circuit, and output of the holding circuit is given to the low pass filter, and output of the low pass filter will be nothing but my demodulated signal, which will be very much similar to my original modulating signal. So now let us try to understand why do you need holding circuit. The PAM signal is discontinuous in nature. It is in the form of pulses. So for example, I've taken one PAM signal. You can see I've shown various pulses which are varying as per the amplitude of modulating signal. The dotted curve, the locus of all the amplitudes joined together, will represent my original modulating signal. So you can see the problem is we have signal in the form of pulses and not the continuous signal, and hence we need something called as holding circuit. So what will be the function of holding circuit? Holding circuit will start its output signal with the very first value, which is the initial value of the PAM signal that enters into the circuit. After that, it will hold that particular value almost constant, or it may discharge a little bit. Now as the second pulse arises, again the holding circuit output will increase to that new value of the second pulse. It will again hold that particular first value with very slow discharge, even in this case, and whenever the next pulse will arrive, again the output of the holding circuit will charge to that particular new value. It will discharge very slowly, and by the time it discharges, the next pulse arrives, and because this time, if let's say there's a negative pulse, output of the holding circuit will go negative and it will continue its charging and discharging process. So why do we need holding circuit is basically to get a continuous signal, and this continuous signal will be almost following the locus of the original signal, because that's how the pulses have been generated. So the amplitudes of the pulses is nothing but representing my original modulating signal. But as you can see right now, when we draw this waveform, which is in black color here, it may not be exactly similar or on the same lines as the original modulating signal shape. That is because we have taken two pulses far away from each other. In practical cases, the pulses will appear at very high frequencies. So two pulses will be very much close to each other, and width of every pulse will also be very small. In that case, the discharging period is very small. By the time capacitor discharges even by a small amount, there will be a new pulse, and capacitor voltage will change according to the amplitude of that new pulse, and hence it will very much follow the locus of the amplitudes of the pulses. Secondly, you can see there will be some sudden changes in the amplitudes whenever next pulse arrives, and this sudden increase in the amplitudes or decrease in the amplitude for negative pulses will represent high frequency components. Now just to remove this sudden increase in the voltage, because it is originally not there in my signal is very much smooth signal, we pass the output of the holding circuit through a low pass filter. So once it passes through a low pass filter, the signal which comes out from the holding circuit will become very much smooth, and it will resemble more to the original modulating signal compared to the output of the holding circuit. So holding circuit, which will give you continuous signal, and low pass filter will remove all the high frequency components in the form of sudden charging to positive or the negative value as the next pulse arrives, and give you a very smooth version of the signal, and that will be my final demodulated signal.